All right. So once again, thank you so much to everyone for coming to this sort of introduction to quantum computing. And oh, oh my goodness, I'm sorry about this. Let me get the chat open so I can see your lovely questions. All right. So as I mentioned at the beginning, this is sort of an introduction to quantum computing. I'm expecting that most of you have little to no familiarity with it. But if you do have some background, please do bear with me as I kind of try and give a decent idea of what's so exciting and cool about quantum computing in the next hour or so. So once again, welcome to Quantum Computing at Davis. These are the sort of members of our organization. Samarth is here with us today. He's the president. Rand is vice president. I am the workshop director, and Tina, who is not here with us today, she's the director of marketing. Samarth, Miranda, do you want to say hi, unmute, and just?
Oh yeah, hi. So I'm Miranda Bell. I'm a material science and engineering major here at UC Davis. It's great to have everyone here.
Yeah, hey everybody, my name is Samarth. I'm the president of the club, and I'm also a material science and engineering student. Yeah, I mean, if again, another thing just I wanted to note is we are still also looking for somebody who can come and help us with sponsorships and talking to various companies. And then we will be opening up for research positions soon. So if either of those things are interesting to you, keep that in mind. We are, trying to add to our team as well within the club. So yeah, happy to answer any questions about that as the presentation goes on in the chat or afterwards.
All right, it's nice to hear from the my higher ups. But so I just wanted to. There's some objectives for our organization if you do decide to stick around for the entirety of the quarter. The primary one that has always been like first and foremost with QCaD is to foster knowledge of quantum computing. So what is it? How can we use it? And how can you guys sort of further explore this field for yourselves? After this, if you stick around, you might better be able to digest a lot of the new sort of quantum research that comes out. I know those papers can be incredibly dense, and there is a bit of a delay between what popular media picks up on versus what papers will present to us. And there's also this unique idea. I've always called it quantum intuition. So if you guys ever take like pre-calculus or algebra, you'll remember your first day was very difficult. Like, oh, I got to find X, I got to find Y, multivariate calculus. They're not inherently intuitive things, but with a lot of practice and a lot of consistency, you can come to develop what I call this intuition, which is you have to take a classical problem. And a classical problem is something that's designed to run on our computers. So if you're using a phone to watch this call or your laptop, that is considered a classical computer. And most of the time, there are a lot of problems that we would try and think of in terms of a classical computer, like something that would run on normal computers. But for the purposes of quantum computing, you have to take this additional step, which is to translate it into something the quantum computer can understand. And as I'll go through this presentation, you'll come to understand why quantum computers are so fundamentally different from our traditional classical computers, and why it's rather tricky to convert a classical problem into something a quantum computer can understand. And furthermore, there are certain properties of quantum computing that you might be able to use to solve difficult problems, problems that maybe classical computers might struggle under that a quantum computer can easily kind of ameliorate. And furthermore, at the end of this presentation, I'll introduce you to these different models of computation. So just as how classical computers, like you have the ARM architecture for mobile phones and devices, and x86 is for like desktops and computers, and desktop computers and laptops, excuse me. Even in the world of quantum computing, which is incredibly young, there are still also a similar sort of degree of variation in terms of these different models. And this is a new objective. This is what I call towards larger things. So if you guys review a lot of the older workshops that I've created, I put a great deal of emphasis on intuition for singular quantum gates. And you can get some neat stuff done with single gates, but the more exciting stuff, the more useful stuff to you will be more complicated quantum circuits or algorithms. And if you don't know what a quantum circuit is, it's just another way of expressing an algorithm. And as I'll go through the presentation, you'll understand what a circuit really means. and quantum patterns. So what I mean by quantum patterns is if you're of a traditional computer science background, you understand, oh, there are for loops, there are these conditionals that I can use. And in a similar context in quantum computing, we do have these kinds of tools or components that are prevalent among almost all existing quantum algorithms, such as probability amplification. You definitely see that in stuff like, I think it's Grover's algorithm, I believe. And if you don't know what that is, don't worry, we'll get to it in time. And I also hope in this quarter to introduce you to these different models of computation. So the circuit model that I keep mentioning gets all the kind of fanfare in the news these days. But there are other models, such as adiabatic quantum computation. And I think Xanadu uses boson sampling. Those are a little harder to understand. And the subset of problems you can use them on is narrower, but they're still very relevant in terms of the quantum computing field, which is so very young and full of potential. So for any, if you want to check out the prior content that I've built before or any upcoming developments, feel free to periodically check out the Quantum Computing at Davis GitHub organization. That's where Samarth, Miranda, and I, as well as many other collaborators, are on here. And you can see my older workshops. There used to be a rudimentary introductory textbook that I composed. It was hosted before. I'll have to get it back up again. But feel free to check this out at your convenience. So with all that introductory stuff being said, here are sort of my objectives for today. I want to give a quick primer in quantum mechanics for those of us that may be a little rusty on physics. I know I'm just a tad rusty there, and what really constitutes quantum computing. So within that sort of loaded question, there's sort of 4 different things that I want to address here. Some of the applications, those models of computation that I hinted at earlier, the different hardware and what challenges there are facing quantum computing, or why is it that we're not using like MacBooks or laptops that have inherently quantum processors in them? What's the holdup? So we'll go back all the way to the origin of quantum mechanics. And there's this famous quote that I always love to share with people as to like why quantum mechanics even exists, or why it's even a thing. So there is nothing new to be discovered in physics now. All that remains is more and more precise measurement. It looks like we have 2 people in the waiting room. I will go ahead and admit them here. I'll move that out of the way. This saying has a bit of an apocryphal origin. There's no positive consensus on where it came from. I think people said it was like Lord Kelvin, and then they moved on to the former director or chancellor of Cornell, or it might have been for the Cornell physics department. But this saying is pretty notorious because this was just when quantum mechanics had not really entered the foray, and many physicists were kind of pretty comfortable, like we've hammered out all there is to hammer out. But that's not so, because late 18th and early 20th centuries, we did have a number of loose ends, like the ultraviolet catastrophe, the photoelectric effect, and the Davis and Germer. Davis and Germer wasn't a problem; it was an experiment, but it was an incredibly pivotal experiment in the field of quantum mechanics. For those of you that aren't too aware, the photoelectric effect, it does have something to do with solar panels. If you've only heard of it in that kind of context, but the basic idea was like if I give you a sheet of metal and I shoot some photons or electrons at it, you'll expect that as you increase the intensity of that of the sort of targeting radiation, that the stuff that gets spewed out of the metal, the radiation or the photons, should increase in intensity. Although that wasn't necessarily the case, and it turns out that all of these have to do, the ultraviolet catastrophe and the photoelectric effect have to do with the fact that there are like in the real world, I can treat things as having this kind of continuous levels of energy, but at the quantum level, you start to run into quanta. The energy levels are discretized. So instead of having like, oh, maybe this energy level can be 60 joules, and it's a huge amount, by the way, but it's just just a tiny, or 60 electron volts, and then the next one can be 60, any number I want. I can't do that anymore. At the quantum level, there are these constraints imposed, and they make sure that things don't, the universe doesn't just fall apart. Although thinking in terms of quanta is an incredibly non-intuitive or very counterintuitive thing to do. So superposition, though, I'm about to go over a number of properties that get brought up over and over in the field of quantum computing and are very, very intimately related to quantum mechanics. So superposition originally, you could argue, starts with this whole argument that began in the 18th century here of light. Is light a particle or is it a wave? And Huygens and Newton both had two very, very excellent arguments for it being a particle and it being a wave. But then Thomas Young does his famous double slit experiment. So you take a sheet of paper with two slits and you'll shine light through it. And the pattern that you get at the end isn't two slits. It's this refracting pattern, much like if you were to have waves of water and you watch those water waves kind of interact with each other, and they can sum or they can subtract from each other, and you get this refractory pattern. I kind of regret not putting an image in here because I know it is much easier to see in person. But so that this sort of like for a while, for the longest time, people thought, okay, light can either be a wave or a particle. So there's the two different parties of physicists were like, sooner or later, we will have like absolute 100% confidence that light will only be a wave or only be a particle. But then Davis and Germer kind of come along, and what they do is they shoot some electrons and perform a very similar thing to a Young's double slit experiment, except they focus more on using these electrons, which we know or we have always thought to be solid particles. And then we find out, holy smokes, it has both wave and particle-like features. So that's kind of like this idea behind superposition. It can be in this juxtaposition or between one state and another. So I give this example here. This ties things back towards the normal realm of computing. So in a classical computer, like the ones we're using right now, you can either have a 1 or a 0 as your value. But in quantum computing, we have a qubit or quantum bit. That is the sort of the smallest unit of computation, is what I call it. And you can have this kind of, you can say like, oh, this qubit may have it might lean more towards 0 than 1. So there's a bit of a probabilistic component there. And there's another property called phase, which I might have to introduce in another workshop. But for now, it's suitable to know that with a single qubit, you can have these kind of probabilistic representations where I could tell you like, oh, this qubit might be leaning 30% towards 0 and 70% towards 1. Like it's almost like if I were to have a quarter and I put the quarter on its side, so then it's kind of leaning between heads or tails. It's not either heads or tails. It can be both heads and tails because it's in this superposition state, which is unique to quantum systems. So you will not encounter superposition in traditional or classical physics. Entanglement is yet another quantum phenomena. When Einstein first heard of this, he was very upset about this. I think he admitted that he called it spooky action at a distance. And if any of you know anything about some of Einstein's complaints with quantum mechanics, he has a very famous saying that God does not play die, because quantum mechanics is an inherently probabilistic phenomena. You don't really have the degree of certainty that classical physics like Newtonian mechanics would give you. And the idea behind entanglement is that you can have two particles, at least two particles, or a system of two particles that are inherently related to each other. And it has to do with how you manufacture them or how you get them to interact. But the idea is if I make one manipulation to say one particle, that manipulation can, regardless of the distance between the two particle systems or n particle systems, if you're a little more intense there, there will be a subsequent correlation, a correlated change to the other quantum system. Now, you have to be careful about the wording here. I said instantaneous. This is technically true, but Einstein and it's already a proven fact that you can't go faster than the speed of light. So you cannot use entanglement for faster than light communication, because if I force a particle on one end to be a certain state, then I essentially break that entanglement. The correlative behavior can only exist within this unknown quantum state. So before I perform an observation. And that's one thing I forgot to mention about the superposition thing, is that you can only have it if the quantum state is not being observed. And what do I mean by observation? And it's probably one of the more confusing parts of quantum mechanics. But when we say observe, we don't actually mean the particles have sentience. Like the particles can't tell that you're eyeballing them with your own, human eyes, or that some other creature is looking at them. It's because for all quantum systems, the only way we can tell the exact value or the configuration of a quantum system is to literally prod it with a stick, which means like we shoot it with an electron, or we introduce some interfering radiation which destroys the quantum state. So if my qubit was like in 30% 0, 70% 1, well, now it's forced to be either 0 or 1. I've broken that superposition. So the reason we can't use entanglement for faster than light communication is because I have to break that superposition. And once I do, even though the behavior between two particles is correlated, that doesn't always guarantee they're going to be like the exact same thing. Like if this thing is if one qubit is in 0 and they're entangled with another qubit, that doesn't really mean like, okay, it's perfectly going to be 0. They're still going to because you've broken the inherent tie in the beginning. Like once you forced one of them to assume a state, then you can't really guarantee the other one. Although in the unknown state, you'll still have that correlation. And this is incredibly useful because there is another theorem here, and this doesn't really get brought up a lot in the context of introducing quantum computing, because this is one of the sort of negatives of quantum computing that you have to. It's part of the things that makes quantum computing very unintuitive, and it's that you can't copy an unknown quantum state onto another quantum state. So if I had like 2 electrons in my hand and they're in 2 different states, and I'm like, okay, well, maybe I want to copy the state of one electron to another, I can't do that, at least when it's in that superposition state. If I observe it, I collapse the superposition, then yeah, sure, you can make a copy, but that's not very useful to us in the context of quantum computing. And this is in stark contrast to classical computing. So let's imagine I have like a bit, and I want to make a copy of the bit. Well, I just do this. I just, I can like I can literally take a wire, I can solder it to another wire, and bingo, I've got my copy of the bit. But in quantum computing, we don't have that. So we have to rely on entanglement, which is this idea that I can introduce some kind of correlative connection between qubits instead of letting them sort of randomly act on their own to circumvent this cloning theorem. So I'm not making a clone, but through entanglement, I can kind of get some of the properties that I normally would intuitively have done through cloning. So it's just a bit of a workaround. Now, with all those properties of quantum mechanics, and I give you kind of a very light taste as to how they tie into quantum computing, the whole goal of quantum computation, regardless of which model of computation you're using, just if you just ever hear quantum computation in any context, is that we want to exploit these peculiarities of quantum mechanics to perform useful computation. And I mentioned there are different models of quantum computation, which is why there are sort of several different approaches to how to do this. But in the back of your mind, do remember that, okay, superposition, entanglement, and this no cloning theorem, which isn't really a property so much as a consequence of working in the quantum mechanical realm. And with all this in mind, the thing that we really want to see with quantum computation, and if you were here a little bit earlier, Samarth hinted at like quantum supremacy, which is this idea that there is an inherent problem that no classical computer can do that a quantum computer can really can actually perform. So we want to make the impossible possible, and we want to make the very slow very fast. Now, this is actually a rephrasing of the same idea. So what do I mean by make the impossible possible? Well, there are problems that if I were to run them on even the most powerful computer in existence, like the most powerful silicon-based classical computer, would take thousands of years. Like by the time I'm dead and my kids are dead and my grandkids are dead, that computer could still be churning the numbers. And this might not just be the size of the problem; it could just be an inherent feature of that problem. But in a more realistic context, especially for problems that we're dealing with today, on a smaller scale, we just want to make slow things go much faster. So that's what I mean by a rephrasing of the same idea. It's just a matter of rephrasing, and that ties in. If you're interested, I encourage you to check out this idea of quantum supremacy. I was saving that for a later workshop, but Samarth brought it up because there was another presentation by another UC Davis faculty member that focused on it. And supremacy is just the idea being that there is a computation that a quantum computer can do that a classical computer just couldn't pull off in reasonable constraints. One of the things before I go into the applications is there's this trait. There's a trait that is true regardless of any model of quantum computation. And it has to do with the fact that you are getting, ta-da, probabilistic answers. So what I mean by this is when you're looking, or when you ask a quantum computer a problem, like let's say I ask it, what's 12 plus 2? If we use a classical computer, the classical computer can say, oh, it's 14, with absolute certainty. And if the classical computer gave an answer like 15, then we can know like, oh, something's wrong with the silicon that the quantum computer is running on. But the reality is with quantum computers, oh wait, did I say quantum? Excuse me. There's a problem with the silicon that the classical computer is running on. I seem to have had a bit of a brain hiccup there, if you'll pardon me. But the idea here with a quantum computer is, let's say I ask the same problem to a quantum computer. What's going to happen is the computer is going to be like, well, I'm 98% certain that it is 14. But there's also a 2% chance it could be 15. And you're like, well, that's a very odd method of computation. Imagine a computer that gives you these kind of answers. But that's inherently because quantum mechanics and quantum computing are probabilistic. Like I told you, qubits can be in a superposition between 0 and 1, which means it's not guaranteed that if you measure it again, it'll be 0. If you measure it again, it'll be 1. So that's where you get terms like BQP. If you're familiar with the computer science parlance, we like to characterize certain problems in computer science as being like P or NP, which just determines their complexity, like how much or how difficult those problems are for our current computers. And there's a special class of problems on these quantum computers, and we're not quite certain about what the relationship is between BQP and NP. And NP problems are on classical computers, they're very difficult to work with. They are very. If I gave you an answer to an NP problem, you can very easily check that it's correct. But if I ask you to solve an NP problem, then the computers can kind of struggle. So we don't really know how BQP relates to NP. Like, is it equivalent? Does it encapsulate NP? And if it does, then that's a good sign. Like, okay, maybe we can translate some of these NP problems into something that's BQP. And if it's a BQP, then hey, our quantum computers can easily pick up on it. And if you look at this chart down here, this is actually the output from a very well-known quantum computing framework called Qiskit. It's IBM's kind of poster child for quantum computing. And you'll notice like, okay, your answers can be in like 0, 0 or 0, 1, 1, 0 or 1, 1. So that's just traditional binary. But there are different probabilities. So like it's like 0.741 probability of being 0, 0, and maybe like a 0.121 probability of being 1, 0. Which is why it's highly likely you have to repeat computations to ensure accuracy. So if you ever work with IBM or Rigetti or another silicon-based quantum computer, they have this idea of shots or trials, and you have to like run the experiment or the circuit, the problem multiple times, and it'll eventually you'll be able to get this information here. You'll summarize what the probability distribution is among your potential answer space. So with that, now that you know that quantum computers give these kind of probabilistic answers, let's kind of jump into some algorithms that are pretty well known. Shor's algorithm has always been as kind of like the attention getter for quantum computing. Like if you don't know what quantum computing is, I guarantee you, like if you're into science fiction or the media, like Shor's algorithm gets repeatedly brought up. And it's fast integer factorization. We can do this. Like this isn't a problem that's impossible to do on classical computers, but if you do it on a classical computer, it takes, oh, this is a typo. It does take a great degree of resources, and it takes some sub-exponential time. And what do I mean when I say like polynomial time and sub-exponential time? Well, computer scientists don't measure the time something runs in seconds. And the reason we do that is because my MacBook may run an algorithm faster than your phone can, or my phone can run it faster than some other model of traditional computation. So as a result, we just focus on how the runtime of that algorithm or problem grows as its input grows. So if I give larger and larger numbers, traditionally that means that the time it takes to solve the problem of factorizing them grows exponentially. And with the latest developments, it's sub-exponential, but it isn't polynomial. Whereas on a quantum computer, it is polynomial. And this is great news. But it's also the reason why Shor gets hyped up so much is because there's a bit of a threat to current crypto systems. So like how our passwords protect our data, and like how like HTTPS, like the protocol that we use to encrypt data as it goes through the internet. Because a lot of our cryptographic systems rely on the fact that it is very difficult to find certain prime numbers, sort of these integer factors for a large number. Although it's very easy to prove that those integers are factors, because I can just multiply those factors, and then you'll get the resulting number. But it's so this is considered like, you could also consider this an NP problem in that it is easy to verify, very difficult to solve. But Shor's algorithm says a quantum computer can do this much faster than a traditional classical computer could. Of course, the problem here, though, is that the media likes to say, oh my goodness, quantum computing is going to be the end of online security or cybersecurity. And that isn't true. Because for Shor's algorithm to really be damaging or threatening, the number of qubits, and remember, a qubit is the sort of smallest unit of computation that you can have. The number of qubits that you need to run a useful instance of Shor's algorithm is pretty large. And we're not at that point yet where we can stably run that many qubits, although with recent developments, we may very well be nearing that. That also brings me to Grover's algorithm. It's lesser known than Shor's, but still very interesting. And it says that we can find a specific input to a black box function that gives a desired output. So a black box function is a function that you don't know the insides of. So I can't look inside the function and maybe exploit an inherent weakness or some unintuitive or counterintuitive property of. That's what black box means. I can't look inside. And the idea is if I give you an output to the function, like if I said f of x is equal to 10, you can use Grover's algorithm to find the input of the function that would give 10. And the interesting thing is this can run in square root of n time. So once again, going back to my explanation here, what this means is that if I give you a bigger and bigger black box or something more complicated, so as the input complexity grows, the time it takes just grows by a factor of the square root of n, where n is just kind of like the arbitrary size of our black box, for instance. Now this is very unusual because here I'm going to go ahead and stop sharing for a quick moment. I think you guys can still see my webcam here. But the idea is, let's say I have this stack of papers. This is my circuits electrical engineering homework. Although if you saw the numbers on here, you could tell I'm not a great electrical engineer. But the scary thing about Grover's algorithm is if I gave you these papers and I said, hey, find a paper with the number 5 on it, we would, classical computers and humans would be like, okay, I'm going to go through, piece of paper 1, 2, 3, 4, and you have to go through it. So the growth should be n. It should be n because this big O notation means worst case scenario. So like the greatest amount of time for any one instance of a problem. But what I'm telling you here is using quantum computing, I don't have to go through all of these papers. I could somehow, without having to check each one, find the paper that has the number 5 on it, which is a very spooky phenomena and something that isn't really easily understood. So with that being said, let's go back to my browser here. And what I mean by not easily understood is not easily understood for those that are not well versed in quantum computing. That's what I mean. And I put this as this is even lesser known, is solving a linear system of equations. This is sort of like a linear algebra thing. You can see like an exponential speed up if you do this on a quantum computer. So these are just some tasters. There are like a slew of other algorithms I haven't covered, mainly because they're very niche, or it's a little tricky for me to give you a real world example where they may be useful, but they are still incredibly interesting nonetheless. And this brings me to sort of the different models of computation. So all sort of quantum computers keep referring to a qubit as the fundamental unit of computation. So a qubit is the equivalent of a bit in a normal computer, except a qubit has those sort of quantum properties like superposition, like no cloning, and entanglement. But your mileage can kind of vary for a qubit because this is when things start to get a little hairy. So I mentioned the gate or circuit model, and the basic idea behind this is to represent an operation on a qubit. We literally draw this kind of circuit. So we apply gates, and as the qubit passes through each gate, it will change the state of the qubit. And that's what we mean by this gate or circuit model. And there's the large majority of existing quantum computing algorithms and research is dedicated to this model just because of how much stuff you can do on it. And even then, though, there are different ways of implementing it. One of them is ion trapping. This is actually probably the, I would assume this like predates some of the more modern silicon-based stuff. But the idea is, okay, we can get an ion or a number of ions, and we can use this electromagnetic field to kind of trap them. And within that trap, we can perform, we can sort of, I think you use a specialized radio pulses to manipulate the state the ion is in. And you can manipulate, you can treat each ion as a qubit. But there's also this silicon superconducting method, which is what IBM, Rigetti, and a lot of the larger corporations do, which is instead of using an individual atom or ion, like an actual quantum particle, you can have, you can represent a qubit using a special configuration in silicon. So this consists of thousands of atoms. So and this goes to testify or to show that quantum phenomena can still very much occur in things that we would not consider inherently quantum level, like we think like, okay, quantum mechanics for electrons, protons, and individual particles works. But you could go to like a Buckminster fullerene. It's like a ball made of like 60 carbon atoms. That's huge, in context of an electron, and still get quantum phenomena. So we can still go even further, and even with existing methods of etching silicon, we can create these kind of greater than sort of atom-sized qubits. So that's what silicon superconducting is, and you can still apply gates to them. That's what I mean by this model. But there's also another class of quantum computing, and I've always called it problem-specific. There's probably much more formal terminology here, but I'm trying to develop your intuition here, and I always think of them as problem-specific. And the idea behind these computers is kind of this bottom-up approach, where it's like, okay, we're going to find one problem, and we're going to do it very well. In fact, much better than a classical computer can do. So the earliest instance I can think of is annealing or adiabatic quantum computation. And this is what D-Wave is doing. And I think it's either Fujitsu or Toshiba that's also messing around with this idea. It still uses qubits, but you're really missing a lot of what the gate model can do. And the idea here is if you represent your problem as an energy Hamiltonian, and you have a okay, Samarth knows a lot better about the Fujitsu side. So Fujitsu's been using this kind of method of computation for drug discovery, which is one of the applications of quantum computing, drug discovery, or a bunch of chemical or quantum simulations that our classical computers can't do. But the idea behind annealing is if I can use my qubits to represent a certain problem Hamiltonian, and I slowly introduce that problem Hamiltonian, it can find the local, it's going to try and find the minima or a local optimum in that Hamiltonian. So if a Hamiltonian, I could try and represent, if it's single variable, it's like a graph, like it might have its own ups and downs, peaks and valleys. And with annealing, I can find, some of those lower valleys, which we would consider optimal solutions. Although this isn't really perfect, and the performance of this method is hotly contested. Like it's, people still argue like, is this actually like, will there actually be a speed up over other models of computing, or is this just, bogus? There's also Xanadu's photonic system. Xanadu is another quantum computing company. They use photons, and photons are great because photons don't really interact, or they're not really susceptible to noise like ion traps and silicon superconducting, because I mentioned these kind of rely on these very highly tuned radio frequency pulses. And if you work with anything in the radio frequency field, you know that your bane of existence is going to be spurious electromagnetic radiation or other unpredictable radio frequency stuff. But with photons, photons don't really, care. I mean, it's light. Light isn't really bothered too much by other radio waves in the air. But with that being said, the only thing it's really sort of good for is this specific problem where you can find the permanent, and the permanent is kind of the opposite of the determinant of a matrix through boson sampling. This is, I will explain this a little more in other workshops, but the idea, just keep in mind that this is a problem-specific method of quantum computation, and it's good at doing one very specific problem, and it can do it very well. And the reason there's this kind of split here is I may have a certain problem, a certain mathematical problem that may translate better to the gate model, or it may translate better to the adiabatic or boson sampling model. You just never know. It's just whatever is easier to get the problem to be translated into. With that being said, with all this really cool stuff we've seen, like these algorithms and these models of computation, you also have a number of challenges, and I think I've already hinted at them in the prior slide. The first thing being is that these quantum computers are very sensitive, at least for the silicon model. So they use like traditional silicon that we see in our classical computers today, like our cell phones and our laptops. Is that they're very sensitive to environmental disturbances. So if you look at a picture of a quantum computer, most of the time it looks like a massive cabinet, because I would argue 80 to 90% of that volume is all cooling equipment, because they have to keep it super cooled and shielded from electromagnetic radiation to ensure they can manipulate the individual qubit states. We also have to worry about the error rate and timing sensitivity. So even though you have these very nice or very strongly controlled environments, it's still possible due to maybe hardware tolerance variability or other factors that your qubit will decohere. It will lose its quantum state. So instead of being in superposition, it just kind of stumbles and collapses. Or it might pick up external radiation and it won't be in the superposition state that you anticipated. Luckily, there's a great deal of research right now into quantum error correction algorithms. So with some additional qubits on top of your existing ones, you're able to detect if an error happened and undo it. Although this is also very tricky to do as well. Connectivity is a problem that you don't really hear mentioned. This isn't a problem for ion-trapped computers, and the reason being is that this connectivity problem has to do with entanglement. So I mentioned entanglement has to occur between two or more quantum systems or particles. And in a normal silicon computer, you'll know how you're confined to a two-dimensional surface, right? So I have to kind of make a trade-off as to how I'll connect 2 points to each other, which means that there are some qubits that you won't be able to entangle with other qubits, and that can kind of hamper your ability to implement certain algorithms. The workaround to that is I can swap qubits. So I'll swap one qubit for another, and I'll shove this qubit closer and closer to a position where it can be entangled. But the more manipulations you do, the higher the chance you'll introduce error into your calculation. So this connectivity becomes a huge deal. But with ion-trapped computers, I can actually individually address different qubits. So it's fully connected, or it's perfectly connected in a sense. So ion-trap doesn't suffer from this. So you might be wondering, well, why don't we use ion-trapped computers, more often? And that's because of this other problem here, scalability. And this is where ion trapping hits the brakes, as I call it, because the amount of equipment that I need to add another qubit scales exponentially, which isn't great. Ideally, we want it to scale linearly, like for a traditional computer. If I want to add another transistor or another bit to my CPU, so it's a 33-bit CPU instead of a 32-bit CPU, the amount of silicon I have to add kind of scales very slowly, which is good. But for ion trapping, it scales exponentially, which is terrible, because that means that to solve a problem, even though the computation may run in polynomial or sub-exponential time, my hardware growth is going to be exponential. So that kind of, it renders your benefit moot. It's like, saying this vaccine will prevent a certain disease, but then in order to take the vaccine, it requires like a gunshot wound. It's just you lose the inherent benefit you had earlier. And that brings me to where we are today. So you'll hear this term brought up a lot, which is NISQ, or noisy intermediate scale quantum computers. this is kind of this gray zone between totally fault-tolerant quantum computers and proof of concept. So by fault-tolerant machines, they're machines that are, oh yes, and Samarth brings up an interesting statistic here of, let's see, 128 qubits versus, 400, it's like 4 million. Yeah, that's 4 million. That's 4 million.
So quantum volume.
Oh, sorry, not qubits, quantum volume. Okay, Samarth's jumping the gun a bit. Quantum volume is another benchmark that's used to determine or help compare how powerful quantum computers are. And there's been a recent development that has like essentially sort of blown this the cap on the highest quantum volume through the roof. Although I think I'll save that for much later. But so what I mean by what we're in between is totally fault tolerant means zero error. So I don't have to worry about the error rate or decoherence or environmental disturbances because the machine can sort of handle that rather, without bothering me and always produce accurate information. Whereas proof of concept is what I'm talking about with like, okay, 1 or 2 qubit, like maybe in the 90s, maybe like the mid to late 90s was like proof of concept. So you had like 1 or 2 singular qubits. So we're in between these two. And as you know, it's any time you reach greater than 50 qubits, it becomes impossible to stimulate or simulate them without using a supercomputer or much larger resources. Or at least, I think 50 qubits, you start to exceed the bounds that our current classical computers can do. Because if you play with existing quantum computing frameworks, what they'll usually do is they'll simulate it locally on your classical computer. So even though this is feasible, you don't get any performance benefit. It's just for your educational purposes. If I want to actually run something on a quantum computer today, I have to, through the internet, submit my problem to one of IBM's sort of publicly accessible computers. And in future workshops, I will definitely show you how to do that. But yeah, so once we reach that kind of 50 qubit threshold, it gets really difficult for us to verify if our simulation or those qubits are correct on classical computers, just because of how it's just very difficult to simulate quantum systems. And part of that has to do with the fact that if I go back to that, the fact that qubits have entanglement and superposition, it's because each qubit represents a huge, an exponential increase in more information than a standard bit in a normal computer does, which is just on and off. Because I have phase and I have this kind of I could be leaning towards 0 or leaning towards 1, so much more information to work with. Now let's see. Oh shoot, that brings me all the way to okay. So that. I guess I forgot to put like an end concluding or thank you slide. But regardless of these challenges, there's still a great deal of work being done to help scale these quantum computers better, to reduce error, and to find new and novel algorithms that can solve problems that we might not have thought possible to be solved on classical computers. Well, quantum computers might be able to step in. So with that little introduction being said, I know I went through a great deal of information very quickly. And I'm certain that most of you may have questions that you would like answered. And if not, I mean, there's a window for Samarth to kind of share what he meant by this quantum volume thing and these more recent developments in quantum computing. So with that being said, I will leave the floor open to any questions you have, or if you think I said something wrong or something was confusing, please feel free to correct me or point that out.
I had a question. So during like a typical quarter, do you guys usually have a project that you will work on together, or do you usually have like individual goals reaching toward like another goal? Just how do you guys usually function practically in learning quantum computing and then also putting it to use?
I see. It's an excellent question. So it's more targeted towards our organizational structure. So for the longest time, I think we've mostly just been catering towards like individual goals. Like we just assume, or we usually try and assume, maybe you're not too familiar with the field, and then I develop all these workshops. There isn't really like an overarching project everyone will pitch into although you're more than welcome to pick up something for yourself, or if you're curious, we can suggest things to work on. But I think the ultimate goal, though, is that once we get people who stick around to a certain degree of proficiency, we can maybe try and connect them with people who need quantum developers or other projects. I think that's mostly in the purview of Samarth and Miranda, who are the kind of administrative higher ups. Because I know my objective here as the workshop director is just to make sure that each and every one of you learns at least it gets a solid understanding of the fundamentals and the algorithms. So you eventually get to a point where you can find things you want to work on and understand them. I hope that's not too hand wavy of an answer. If you're not satisfied with that, do let me know.
No, that was great. Thank you.
Yeah, no
I
problem.
could probably go into some more depth on that in terms of like what kind of projects and like how we are trying to structurally go towards solving that problem of like, connecting you with opportunities to really grow your skills. So in terms of what membership looks like for the club, membership just really means attending the workshops or participating in one of the research projects or both. But in terms of actual project work, the current projects we have under development are all kind of focused on biology. This is more because I was interested in that, and I talked to some folks at IBM, and they said they'd be happy to help fund it. And so we started to work on the kind of project and got some people together who were focused on biocomputational work. So a project that we've been running since April is on how we can map biological molecules into quantum computers, where John was helping out, as well as another guy named Jack Goon, who is a researcher who worked with the Rosetta toolkit for protein folding in the Siegel lab on campus. So them, as well as me, worked together into making a package for mapping biomolecules to quantum computers that's actually used by some of the researchers at IBM's life science division today. And then a project that we're trying to get up off the ground is a project related to protein folding. So taking that package that we built and essentially making it better so that we can actually do protein folding work with that is something that we're trying to get together. We're trying to make this a inter-university kind of collaboration because it's going to be a very tough project. And we're trying to get the best of the best in protein folding and as well as quantum algorithms together to do this project. But it's open to anybody, undergrad up to PhD students, and who has the skills or has interest to put in towards a project, depending on what kind of skills we need. But I'm waiting to hear back from IBM to see if that project will actually go through, and they'll be able to fund that, because we're looking for that to be like a funded internship kind of a thing. As far as other smaller projects that are not so ambitious and kind of things that we're hoping to do, I mean, I also want us to collaborate more with the there's another class at UC Davis that is being taught by Professor Radulowski on quantum computing, and I know that she's having a lot of her students work on final projects where they're going to be working with QCaD and with a lot of these toolkits. So we could have, if you're interested in working on projects that are a bit smaller and kind of have an end date by the end of this quarter, that's a project pathway as well. You could be working with some of the grad students on a project like that. And last but not least, we want to help you connect with some of the researchers on campus who are doing quantum research. So we're going to collaborate with the Physics Club on a quantum math and physics workshop with the Quantum Math and Physics Center, hopefully within the next month. So hopefully through that, you can meet some professors on campus who are looking for new students and work with them. Or at least they'll give you some good ideas so that you can, do a project within the club and with some other students. So yeah, it's pretty open. We're not trying to be oh yeah, you need to show up to X number of events and you need to do Y number of things, and this is how you'll become a member, because it's such a new field, right? We can't exactly tell you, hey, this is exactly what you need to do to be successful, because there really is no one pathway there yet, right? So yeah, just let us know if you have any questions and any way we can help.
Hey, Samarth, do you want to go ahead and put the link to our Facebook group in the chat? It looks like there's someone who's interested in staying up to date with some of our future workshops and announcements, because we do have a mailing list and a Facebook page. So with Samarth introducing some of the cooler things you can work on in the organization, I'm still open here for questions. Looks like we still have 8 minutes remaining. If there's anything I seem to have gone over too quickly, I know sometimes I might talk a little too fast, but it's because I'm super excited about the field, or if I didn't explain anything as clearly as you hoped, don't hesitate to go ahead and pose your question. Oh, and I also put a link to some of the prior workshops and stuff that I've done. Okay, let's see what skills would be necessary to join projects, both the bioquantum stuff and the similar projects. Knowing about Qiskit and quantum gates be enough. That's definitely a nice and healthy start there. I'm hoping to go over like some of the stuff behind the algorithms. Like algorithms is sort of like the culmination of all your knowledge of quantum computing. So I think the goal here is that if you stay long enough, you will get that knowledge, or at least I will be able to give it to you in a more digestible format, because I know many of you may have a stronger inclination to math than I do. If it's of any comfort to you guys, I haven't always been the strongest math student, but I seem to have a decent grasp on quantum computing. Alex asks if the recordings will be posted online. Yes, they will. There is that website that you saw earlier, like the one with my kind of GitHub URL on it. If you scroll up a bit, I always post a link to the video, the slides, and in future workshops, you will get the I will also have the links to the code. I appreciate your kind words. I'm flattered. Project collaborations only for use. Samarth, do you want to speak to that? It looks like Vinuth here has I'm not too certain on your policy with that.
Yeah, good question. I know that a lot of you joining are not UC Davis students, and thank you for coming. Honestly, I'm really happy to see that we're getting a great audience from all over. And with regards to projects, if it's not funded by the school, then yeah, sure, we'll leave it open. I think with the protein folding project, we definitely are looking for it to be like a collaborative effort, specifically with schools who have experience in either protein folding or quantum algorithm work. So if you go to a school that has kind of experience in that, or you yourself have good experience in that, or have some good ideas of ways we can do this work together, then sure. I mean, I don't see why not. In fact, I think right now I penciled in that it would be between Davis, UCSF, Washington, Harvard, and Washington University. So quite a diverse group of schools across the country. Just because I've had conversations with the professors and the students at all these places, or I've seen work from their schools where it's damn, if they're not part of this conversation about protein folding on quantum computers, it's not going to happen properly. So yeah, where are you joining in from, Vinuth?
Hey, hi. I am joining from University at Buffalo.
Wow.
Oh, nice. Yeah, I know that they do some cool bioinformatics work there, right? You guys have your own server and whatnot. I think I was playing around with.
I'm not sure.
All right. Well, let's see if there are any other.
Thanks for the answer.
Oh yeah, let's see. Explain more on silicon superconducting and how it works. Okay, so the reason I've been skirting around, there's a question here that says, can you explain some more on silicon superconducting and how it works to perform quantum effects? And that's an excellent question. And the problem is there is no very nice explanation that I can give in the next 3 minutes. The reason being is that it requires you to understand how a Josephson junction works. So if you're curious, you can look that up. But the idea is there's this, I know it's, oh man, how do you explain it? But I mean, the idea is that once you have that junction implemented in silicon, you can you can apply a number of controlled pulses to it that will enable you to represent or have those quantum effects. I have very intentionally not bother to tell the underworkings just because it's so it's a bit marred in some finer physics related stuff. Although I wouldn't, now that you brought it up, I wouldn't hesitate to bring it up in the next workshop. I will make that a priority to have an explanation to you by the next presentation. And in the next presentation, I'll also be going over, I'll try and spruce up some of my older workshops. So they'll be ready for you guys to play around with, and you'll be able to get your feet up and running on the gates stuff, because this quarter's emphasis is more on algorithms. I spent the last quarter focusing a lot on singular gates and their logic. Yeah, no problem. Thank you so much for asking that wonderful question. Yeah, that is, sometimes the hardware behind quantum computing can be more difficult to understand than some of the algorithms, but we will definitely get there in time. I definitely hope so. I have high hopes, and I fully intend on carrying through with them. All right, looks like we have another 2 minutes here. Any other questions?
John. So for anyone that is interested in research, I apologize if the mic is weird. I'm in my kitchen. If anyone is interested in research, it doesn't have to be computational. It can also be experimental or even theoretical work. And we have had, we've definitely had experimental. We're most definitely going to have someone who is computational this quarter. Hopefully, if they say yes. Obviously, with COVID and everything, life has been a little bit weird. So yeah, don't worry. Don't think, oh, I don't want to go into a computational field, because right now I'm in a experimental / I guess I am slightly in simulation / computational because of COVID. But before that, I do photonics research, so I actually build like optical setups and things like that. So you don't necessarily need a computational background.
All right, we got another 20 seconds. But I'm incredibly happy to see how many people have decided to come to get sort of an introductory grasp on quantum mechanics. I definitely hope I was able to convey some of the more fundamental topics, and that it was of interest to everyone who attended, and that I will be able to see you guys hopefully next week, where I'll be hosting my next workshop. I will be going over those pesky gates. So yes, we are settling on for now, we're settling on the circuit model of computation, just because of how universal it is. Although later on in the quarter, I may decide to introduce you guys to some of the, I would say, like problem-specific methods that I mentioned earlier, such as adiabatic and boson sampling. All right, I think that that concludes sort of our first meeting for the day. Once again, thank you so much for your time. I hope you guys all have a wonderful weekend, and stay safe.
Yeah, thank you. Have a good night.
Thank you everyone for coming.
Thank you.
Thank you.